Chapter 3. We are now venturing into exponentials. So we will talk about exponential growth and decay in 3.1. Specifically, we use a lot of exponential models to model physical systems and population models, i.e. bacteria reproduce at an exponential rate. The example that I'm going to talk about is more like cell division, where say you have a population that regularly doubles. So the cell, right, basically builds up enough material and then it splits into two cells. And so if we take that idea, that is what happens with exponential growth. If you only have one and it gets ready and it splits into two, now you have two. Then if both of those do the same process and split, now you have four. And if they continue to do that, those 4 become 8, and then those 8 become 16, and those 16 become 32, and so forth, if it's regularly doubling. That's exponential growth. So this specific case corresponds to an equation y equals 2 to the x. So if we talk about it algebraically, that would be an equation that models this behavior, if it's continually doubling. You can verify that these numbers are consistent by just substituting them into your calculator, right? If I substitute x equals 0 into this equation, then I have y equals 2 to the 0. 2 to the 0, if you substitute it into your calculator, will get you a 1. For x equals 1, 2 to the 1 gets me a 2. 2 squared gets me a 4. 2 cubed gets me an 8. And that process continues. 4th, 16, 5th, 32. Notice that in each of these cases, when I go from 1 to 2, I multiply 1 by 2 to get 2. When I go from 2 to 4, I multiply 2 by 2 to get 4. When I go from 4 to 8, 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So this multiplying by 2 is what's happening in each instance. And that corresponds to the number 2 in the equation, 2 raised to the xth power. We can determine these values. Additionally, so in this case, our initial value is the same as it was when we did lines. We started at x equals 0, and we only had 1. That was our initial population. It's also our initial value. And you can find it the same way. You substitute x in, and you solve for y. For us, for y equals 2 to the x, it was 1. Something called the growth factor is the 2, right? The growth factor is what we are multiplying by in each of those cases. So the steps that I broke out, I said multiply by 2 between each step because the growth factor is 2, so you multiply by 2 every time you add 1. Generally, when we substitute these into an equation, the initial population is your c value for y equals c times a to the x, and a is your growth factor. We consider x to be time or time intervals for how many times this population has, say, doubled in the case of our example. In general, it's going to be multiplied by a, whatever a is. To give you a peek of what this looks like, if you graph the equation y equals 2 to the x, this is what it looks like here. You can graph it on your calculator to verify that. But you can see that this is not at all like linear, right? It's going towards 0 on the left, and it's growing very rapidly on the right. So we'll actually have a section where we compare exponential and linear models later. Now that you have an idea of what an exponential model looks like, if I give you a problem, you can determine what the exponential model is that suits that. So for example, if we want to determine the exponential model for a tumor that starts with only 20 cells, but it quadruples every hour. So now your time interval, your time is in hours, that x value. We know that it's quadrupling, which means we multiply by 4 every hour. And we initially start with 20 cells. So our initial population will be 20. we can model that exponential growth per hour through the equation f of x equals c times a to the x. In this case, c is our 20 cells, and a will be 4 because quadruple means times 4. So f of x is then, if I substitute that in, just 20 times 4 raised to the x power. Be very careful about your order of operations here. 4 is being raised to the x power, the 20 is outside. It is being multiplied after the 4 has been raised to the x power. So I could imagine that I have parentheses there, because that happens before I multiply by 20. Now, if I ask you a question about this, say, what is the population after 3 hours? Then I would just substitute in, like we did with linear models, the 3 hours into the equation. Since this is a population in terms of hours, I just substitute 3 in for x, 20 times 4 raised to the third power, or 20 times 64 to get me 1,280 cells. So in just 3 hours, I went from 20 cells to 1,280 cells. That is an example of exponential growth. Now, if for some reason you're given a problem, but they don't tell you a rate at which it's growing explicitly, you can find it by taking the ratio between terms. So if you remember in that earlier table, I showed you that it was multiplying by 2 again and again and again between each of the steps. I can do that to determine my a value. I can look at the ratio of the next term to the current term, right, f of x plus 1 over f of x, in order to find what my a value is. So if I know that I have 27 cells at hour 3 and I have 9 cells at hour 2, then since 3 is 1 greater than 2, then my f of 3 is my f of x plus 1 and my f of 2 is my f of x. And I can find a by looking at f of 3 over f of 2 or looking at 27 over 9 to get me a 3. So if that had been the system I was modeling, I would determine that the growth factor is then 3. Modeling exponential growth, we often talk about a growth rate. This is different from your growth factor. This is a rate at which the population is increasing, so it's usually in a percentage, which means that instead of telling you that it doubles or triples or quadruples and so forth, you would say that it's growing at a rate of 20%, 15%, 10%, something like that, where it isn't just doubling or just tripling. So your growth rate is typically your growth factor minus 1. So if it were doubling, your growth rate would be 1, because you would be increasing by 100%, right? What I have plus 100% of that again. And that makes sense when you think about it in that context, right? I'm getting 100% more at every interval. Now, if we take a look at an example, so for example, if our population in Denver was increasing by 20% each year, determine the exponential model, its growth factor, and its growth rate. So first, we want to figure out the model. So if our initial population is 600,000, after 1 year we will have an additional 20%, which you find by multiplying 0.2 by that 600,000, right? That gets you 120,000 more people, and that makes it a total after 1 year of 720,000. It's growing very rapidly. This is probably not anywhere near what we actually have. Now, the next year, if it does that again, we grow by 20%, we have an additional 20% again, but now it's 20% times our current population of 720,000, which means we add another 144,000, which now brings us all the way up to 864,000 people, which is getting pretty tight here, right? So this is how we can talk about it in the context of the growth rate. This is what you're doing, right? That's not generally how you calculate it algebraically, because you actually want to construct a model that is exponential. So if we define this through f of x plus 1 is equal to f of x plus the 0.2 times f of x, we can combine the 1 and the 0.2, so we have 1 plus 0.2 times f of x, or 1.2 f of x. This number, the 1.2, is our growth factor. That's the thing we're used to, right? F of x plus 1 divided by f of x is 1.2. That's our growth factor. Our growth rate, remember, is our growth factor minus 1. If I subtract 1 from 1.2, my growth rate is 0.2, or hey, that looks like that 20% that we were adding at each step, right, each year. So your growth rate is typically just defined by the percentage increase that is defined in the problem. So in answer to all of the questions for this problem, the exponential model would have been the initial value, 600,000, times 1.2, which is the growth factor, raised to the xth power, and our growth factor was 1.2, and our growth rate was 0.2. The opposite direction, we also have exponential decay, and this does also model a lot of systems. So exponential growth corresponds to something that's growing very rapidly. Exponential decay corresponds to something that is decaying, but it's not decaying rapidly, it's decaying at a rate that corresponds to its what would be growth factor, but is now decaying. So in these cases, if A is between 0 and 1, it's decaying. You are taking a fraction of whatever you originally had. This is pretty common for radioactivity, pharmacokinetics, which really just means the quantity of drug in your system. It's also used for decaying populations. So say there's a predator in the area and it's killing off a certain quantity of the population at a consistent rate. You can use exponential decay to model the decay of that population, using, once again, A between 0 and 1 to correspond to how much of that population is still alive at each time interval. For growth, you may have noticed that our A was always greater than 1, right? We didn't explicitly say it, so I'm saying it now, but if it's growing, A is greater than 1. Your growth factor is bigger than 1, so you are actually growing, because if you multiply by a number that's bigger than 1 every time, you are going to see growth, and if you multiply by a number that's smaller than 1, you're going to see it get smaller each time you multiply by that number, right? Because 1 corresponds to it staying constant. If I multiply by 1, it doesn't change. Multiply by 1 doesn't change, right? Again and again and again. So let's take a look at an example. I'm going to do a pharmacokinetics example. If, say, a patient takes 200 milligrams of ibuprofen, because that's a common over-the-counter pain reliever, and say that 20% of that is expelled by the body at each hour, let's construct the exponential model for the dosage in the patient's system at each hour, knowing that it's decreasing by 20%. So now we use that concept of the growth rate in the context of decay. So if it were increasing by 20%, it would be positive 0.2. But if it's decreasing by 20%, our R value, which is our growth rate, will be a negative number because it's decreasing by 20%. So negative 0.2 is R, and remember that R is A minus 1, so A will be R plus 1, or 0.8. It's consistent with what I said above, where A needed to be between 0 and 1, right? A is 0.8. We keep 80% of it at each time interval. And the initial dose was 200 milligrams, so our C value is 200, getting us a model of 200 times 0.8 raised to the x power. Now, there's our model for exponential decay, and if you want to, I highly recommend graphing this on your calculator just so you can see what it looks like. How much is left after 4 hours? I'm going to do the same thing I'm used to doing. I plug in 4 for any x values that I have, 200 times 0.8 raised to the 4th power. If you do that, again, be careful of your operation, 0.8 raised to the 4th power, and then multiplied by 200. You have 200 times 0.4096, or about 81.92 milligrams left in their system after 4 hours. What is the half-life? This is a question that, depending on your major, you may already be familiar with this concept of half-life. It's the time that it takes for the dosage to reach half of what its value currently is. And so that means that 1/2 of my initial dose in this case was 1/2 times 200 or 100 milligrams. So if I want to figure out at what time I'm at 100 milligrams, I would set that equal to the equation, right? 200 times 0.8 to the x, getting me a 1/2 equal to 0.8 to the x. But you don't actually have a way to get the x out of that exponent. Like right now, you don't have the material to actually solve this equation. That's okay, but I want to give you some sort of flash forward that this is something that we're heading for. In chapter 4, we'll introduce logarithms and we'll be able to solve for x explicitly, but in the next couple sections, we'll talk about a way to determine this so we can actually determine things like half-life in another way, maybe. But chapter 4 will actually get to solving this explicitly, which is very important for application purposes. So we'll build to answering this question over the next few weeks. Let me know if you have any questions, and I will see you in class.